I'm Bill Heffernan from the Electric Power Engineering Centre at the University of Canterbury, and I'd like to present this paper with my colleagues Ben Mitchell and Michael Hayes, both from the Department of Electrical and Computer Engineering, also at the University of Canterbury, and describe our development of a trapezoidal current generator for an electromagnetic groundwater flowmeter. This work is part of a larger program funded by the New Zealand Ministry of Business, Innovation and Employment under the New Zealand National Science Challenge program. And the paper is part of a collaboration between the University of Canterbury and also Lincoln Agritech, Robinson Research Institute of the University of Wellington, GNS Science and the Department of Physics at the University of Otago, which are all New Zealand institutes. The overall project seeks to answer whether electromagnetic flow metering can be applied to underground aquifers where the structure of the flow channel is not known and where the speed of the water can be extremely slow. We've built a mini Aquifer Rig in our laboratory, and this consists of a perspex tank across which water can be made to flow very slowly, with electrodes placed in the water to measure the voltage produced by the flow of ions in water moving through the magnetic field created by an air-cooled coil. This paper concentrates on the implementation of a trapezoidal current generator, which is designed to produce 4 millitesla field at the electrodes in the tank. And it does this by driving 50 amps through the 8.4 millihenry 68 milliohm coil. Those are both experimentally measured values. It attempts to produce a trapezoid of at least 10 Hertz, and the reason for this will become apparent. It's essentially to minimize the 1/f electrode noise, and the flat portions to try and maximize the VDT and DIDT free portions of the waveform to minimize second order coupling effects from electric field and the transformer effect due to Faraday's law. The power spectral density of the electrode system has been measured and also modeled as shown in this diagram. Clearly, if we go above 10 Hertz or preferably even 20 Hertz, we will improve the noise performance of the system. But if we want at least 50% of the current waveform to be steady DC, i.e. flat top or flat bottom, we need to keep the current transitions from 0 to full scale and from 0 to negative scale and vice versa less than 12.5 milliseconds to give an overall half cycle time of 50 milliseconds, i.e. for a total cycle time of 100 milliseconds or 10 Hertz. Very simply, because V equals LdIdt in the coil, this can easily be shown that we need at least 34 volts to get the required DIDT to give us the required delta T of less than 12.5 milliseconds. The current generator consists of the components of this schematic diagram. Essentially, we have a constant current, constant voltage source at top left. We feed this into a power switching circuit, and the result is fed to the coil. To control this, we have a control circuit which controls the switches in the power switching circuit. We have some feedback to the control circuit from a current sensor, which is sensing the current from the constant current, constant voltage source, and we have a power supply to run everything from. This diagram shows what's inside the power switching circuit, and this is what I concentrated on, with the microcontroller-based control circuit being implemented by my colleague Ben Mitchell, and the analysis of the circuit operation being carried out by my colleague Michael Hayes. So in the power switching circuit, we can see again our model of the constant current, constant voltage source at the left-hand side. And in particular, we notice its output capacitance C2. This will come back to bite us later on. D1 is just there as protection against reverse damage to the power supply. Doesn't take any active operation in the circuit. We will see QR1 and R1, which comes into operation later on, which is a damping resistor and the switch. TVSs are to clamp the voltage across the bus there in the case of rapid DIDT and the voltage it causes across stray inductance during switching of the devices towards the right, which we'll come to. D2 is necessary to make sure that C1 cannot discharge back into the output capacitance C2 of the voltage source. C1 itself is a resonant capacitor and it has a bidirectional switch in series with it. This provides the magnetizing energy for the coil, and it also provides somewhere for the energy in the coil to go back to when the coil demagnetizes. Now the coil we can see on the right hand side, which is air cored. As we can see, it has 8.4 millihenries of inductance and 68 milliohms of series resistance. It is in an H-bridge so that the current can be made to flow in either direction through it, and as I say, by judicious switching of the switch in series with the capacitor C1, we can shuttle energy between C1 and L1. Here we can see the control sequences which are implemented by the control circuit. The first line only occurs at the beginning of operation, and it's simply about charging up the resonant capacitor C1 to the same value as the constant current, constant voltage source voltage. The second line refers to the magnetization and steady state periods. It's specifically for a positive half cycle where switches QA1 and QA2 are in play. The negative half cycle is very similar, except switches QB1 and QB2 are used to pass the current in the opposite direction through the coil. This period, there is a period stated here, variable called T positive, which is the duration of the flat topped part of the positive half cycle. And you'll notice it refers to stage letters, and we'll see very shortly what those mean. Now the third line here is the demagnetization part of the waveform and the zero current period which occurs between successive half cycles. And you'll also notice another, that's TZC is the variable there, which means the zero current period, which can be set to from anything from very small to as large as you like. T001 is a dead time set to 100 microseconds in our simulations and practical circuit to avoid shoot-throughs of the switches in each of the legs of the H-bridge. As noted before, switching circuits can generally be described by a number of equivalent circuits through which they pass as the conducting switches change. In this slide we can see stage A, which is where all we're doing is charging up the resonant capacitor C1, which only happens at the beginning. Then the circuit goes into a sequence where it passes through stages B, C, D, E, F, and then back to B again sequentially. And we'll note that on the positive half cycles, the semiconductor devices marked in red are those that conduct, whereas in the negative half cycles, it's the ones in the blue which are instructed to turn on by the control circuit. This particular case of stages is where the equivalent circuits look like this, is for the very special case, which cannot unfortunately be realized in practice, where the output capacitance of the constant current, constant voltage source C2 is equal to 0. The circuit diagram as simulated in PSCAD EMTDC with C2 equal to 0 is shown here. Note that switch QR1 and the damping resistor R1 are not switched in this circuit simulation. In the top simulation waveform, we can see the coil current as we leave a negative half cycle, go into a zero current period of just over 100 milliseconds, magnetize in the positive direction, sit on T positive of about 350 milliseconds, demagnetize again to another 100 odd millisecond zero current period, and then remagnetize in the negative direction. This is all slowed down on purpose to give a half cycle of about 500 milliseconds for a full cycle period of 1 second or a frequency of 1 hertz. In the bottom waveforms, we can see V1, which is the voltage across the constant current, constant voltage source, shown in the blue waveform. And it's quite hard to see, but the green waveform, which goes slightly higher during the zero current periods, is the voltage across the bridge, which during the zero current periods is the same as the voltage across the resonant capacitor C1. So during the demagnetization, we can see the resonant capacitor voltage increase and then stay there during the zero current period and decrease again during magnetization as its energy is put back into the coil. During the flat top periods of the waveform, we can see that the source voltage is in the constant current mode. It's basically the voltage drop across the coil's internal resistance. Now, unfortunately, these waveforms, although they look absolutely exactly what we want, they cannot be realized because the output capacitance of the power source cannot be zero in practice. Given that the only power source we had available to do the constant current, constant voltage source duty, which was large enough to provide 40 volts and large enough to provide 50 amps, actually has a measured output capacitance of 27,000 microfarads or 27 millifarads, we decided to simulate this case. And again, the damping resistor switch QR1 is not closed in this simulation. As one might expect, now that we have quite a large output capacitance of the power source, we can see that unfortunately that capacitance of course rings with the inductance of the coil. So C2 rings with L1, and we can see that in the current waveform through the coil, and we can also see it in the voltage waveform across the power source. So that obviously does not give us a nice flat-topped current waveform, so we must get rid of that ringing, and we can do that by switching in that damping resistor R1. Redrawing the equivalent circuits from slide 9 for the case where the output capacitance of the voltage source is not zero, we see that stages B and C, in which the damping resistor R1 is switched into the circuit, become more complex, and we can see how R1 damps the circuit, resonant circuit formed by C2, the output capacitance of the source, and L1, the coil's inductance. Here we see on the top trace the resonant capacitor C1 voltage. On the left hand side, going from the constant voltage of 40 volts up to its peak value, is the demagnetization period. In practice, there would then be a zero current period at which the capacitor voltage would stay at that value of about 40.5 volts until TZC zero current period is over. Then the magnetization period begins, and the capacitor voltage falls back to the constant voltage value of 40 volts. This has just been shown as a single function with no time, zero current time in the middle in this graph. In the lower graph, we can see the coil current, and this is going from a negative half cycle on the left hand side through a non-existent zero current period at the middle, and then into a positive half cycle. Now you will notice that it does not quite reach the set point of 50 amps by the time the capacitor voltage has fallen to 40 volts, so this is of course due to losses in the resistance of the coil. Now the value of current that it actually reaches during this magnetization point is the end of this stage, stage F, and marks the beginning of stage B, so we can calculate that to work out the initial condition of coil current for stage B. Having calculated the value of coil current I2 at the end of stage F and the beginning of stage B, we can then analyze stage B with the help of the LCAPI program referenced in the paper, It can be shown that the coil current I2 in the S domain is as shown, and it can also be shown that by equating 0, 1 and pole 2 in the pole 0 gain expression shown here, we can achieve optimum damping. Now what we've also shown in this is with optimum conditions for a range of different values of source capacitance C2 and a range of operating constant voltages V set, we can calculate the value of the set point current, the damping resistor R1 and the efficiency. And we can see that as C2 gets larger, for larger power supplies, the value of I set we need to set gets higher and higher, and the efficiency gets lower and lower. Now the available power source to us is the one with the 27 millifarad output capacitance. The same company make two smaller sources, both of which would be capable of driving this coil, which have smaller capacitances of 8.5 millifarads and 2.5 millifarads. Unfortunately, we don't have those, so we have only looked at the one we do have, the 27 millifarad case here, and we've shown during stages B and C the coil current achieved with the optimum damping resistor R1 choice as a function of three different set point voltages, 30 volts, 40 volts and 50 volts. With the necessary value of R1 determined from the LCAPI analysis, we are then able to enter that into the PSCAD EMTDC simulation of the case with the 27 millifarad output capacitance of the source, 40 volt set point, and the chosen R1 damping resistor value of 28.2 milliohms to give optimum waveforms. The simulated coil current waveform is again shown as the top trace here, and as we can see, it does look nice, exactly what we wanted, and it's set for the same period and frequency as our previous simulations. But if we look at the lower trace, which is actually showing the current I3 that flows through the damping resistor and hence the damping resistor switch QR1 as well, it has a peak value of getting on for 1400 amps, and if we look at this waveform in detail, we can show that it exceeds the safe operating area of the QR1 that we have actually realized on our practical circuit, which consists of three large Infineon power MOSFETs in parallel, but this is too big for a single pulse. So, as our hardware is not capable of providing the optimum damping with VSET of 40 volts, we simulated the case with 30 volts where we believed that the necessary damping current would be within the safe operating area, and our calculations show that here the ideal choice of damping resistor R1 is 46 milliohms. Again, the coil current is shown in the top trace, and it does indeed achieve the nice flat topped optimally damped objectives. And if we then look again at the damping resistor and damping switch current at the bottom, we can see that there is a peak value of somewhere around 550 amps, which is now, and this waveform is now within the safe operating area of our implementation of QR1, so we can go ahead and actually make this happen on the real circuit. These waveforms were recorded with a digital storage oscilloscope from the practical implementation of the circuit. The top waveform, of course, is the coil current, which is pretty close to optimally damped. The second is actually the voltage source output, so it actually includes the damping current and the coil current, so hence it's a little bit higher than just the damping current shown in the simulation. And the bottom trace actually shows the voltage across the coil, from which you can see the magnetizing and demagnetizing voltages applied across the coil, and the steady state much lower voltage where the voltage is only driving the current through the coil resistance with no DIDT. Now we can notice that the actual value of current achieved through the coil is only about 41 amps instead of 50, And to get the optimum damping, the actual experimental value of damping resistor R1 is about 40 milliamps, so rather less than the simulated value. It's actually quite difficult to achieve a power resistor that will be as small as that, take the current necessary. And for this circuit to work properly, it has to be very thermally stable. It can't be drifting around as it gets hot. Also, for the circuit to work well and symmetrically in positive and negative half cycles, all the resistances of the physical bridge layout, including a matching of the MOSFETs, any circuit tracks and so on, need to be very symmetrical, otherwise you won't get symmetry in the current waveforms. And it's quite clear to see that this circuit becomes more sensible for lower values of source output capacitance C2. And essentially it shows us that the source we're using, which is actually rated for 510 amps and 80 volts, although not at the same time, a 15 kilowatt power limit, is quite a lot bigger than we need, and that's why the C2 is excessively big. So to conclude, we can show that we have built a return to zero trapezoidal current generator for driving an electromagnet. We've developed it, simulated it, analyzed it, built it and tested it. The circuit described uses a single constant current, constant voltage power source, a large resonant capacitor C1, a number of power MOSFET switches implemented as described in the paper, a current sensor monitoring the power supply, power source current, and a microcontroller-based switching control system. One of the main attributes of this circuit is that we have to discharge the power source's output capacitance as we transition from constant current to constant voltage mode, and this requires switching in a well-controlled damping resistance each half cycle. If the output capacitance of the source is large, there's a lot of current flowing through that damping resistance and the circuit efficiency suffers. There are other circuit topologies, at least two of which we have realized, which we hope to be reporting on soon, which overcome some of these limitations. Many thanks for your kind attention. I'd like to acknowledge the help of the individuals shown on this slide in achieving our project aims. I'd be happy to accept any questions by email at the address shown. Thanks and goodbye.